Predicting the future, it's one of the oldest human endeavors, right? From ancient oracles to today's, well, very complex models.
Definitely. And we're seeing large language models get incredibly good at some really tricky tasks.
Yeah, like finding coding bugs, solving tough math problems. So you start to wonder, can they actually get good at something as, well, messy as real world forecasting?
And that's exactly what makes this deep dive so fascinating. We've seen huge success with things like reinforcement learning, with verifiable rewards, RLVR, in areas where answers are really clear cut.
Right, like getting a math problem spot on or making sure code compiles perfectly. You get that instant objective feedback.
Yes, that nice clean signal, yep, work, or nope, failed. Simple.
But predicting complex real-world events, that just feels like a whole different ballgame. The outcomes are often binary, sure, yes or no, but the feedback.
Ah, the feedback. It's delayed, for one. You don't know the outcome right away. And it's often noisy, influenced by tons of unpredictable factors. Certainly not instant.
And that specific challenge is really what the sources you shared dig into. This deep dive is all about a study that took RLVR and, well, tried to adapt it for that notoriously difficult problem forecasting in the real world.
Exactly. It's about applying these advanced techniques where the ground truth isn't so neat and tidy.
So, our mission today is to really unpack the academic core of this work. What are the specific, kind of nitty gritty challenges RL faces when it comes to forecasting rewards?
And crucially, how did these researchers get creative? How did they adapt the algorithms, the training methods to try and overcome those problems?
Right. And what do the findings actually tell us about turning these sophisticated AI models into genuinely valuable forecasting tools? We want to focus on the innovative academic details here and why they really matter.
Let's get into it.
Okay, let's jump right in then. You mentioned that feedback issue. Why is applying RLVR to forecasting so fundamentally different from, say, a machine learning perspective than solving a math problem where you know instantly if you got it right?
Well, what's really fascinating, I think, is the nature of that reward signal the model gets. For math or code, it's objective, right? Instantly verifiable, pass or fail. Did the code run? Yes. Did the equation balance? No, right now.
Clear as day.
But forecasting, the outcome, the event happening or not okay, that's binary yes, no. But you only learn that later. The reward is fundamentally delayed.
Okay, delayed reward. That makes sense.
And on top of that, real-world events are messy. They're influenced by countless factors, things you just can't foresee. So that creates noise in the signal. The model's prediction might be perfectly logical based on the data it had, but some random event throws it off, makes it technically wrong.
Huh, so the model is trying to learn from feedback that's, what, sparse, arrives late, and isn't even perfectly clean or reliable. Why does that cause problems for standard fine-tuning approaches?
It makes those standard methods quite fragile. Brittle is the term the study uses. That sparse, lag, noisy feedback loop makes it incredibly hard for the model to effectively connect its actions, generating a complex rationale and prediction to that eventual distant, messy outcome.
So the learning signal gets kind of lost in translation.
Pretty much. Standard fine-tuning just struggles to extract a clear, useful learning signal from that kind of environment. It's not built for that kind of ambiguity.
And importantly, the goal here isn't just a simple yes or no guess, it's about probability. There's a 70% chance this happens.
Exactly right. Probabilistic forecasting. The model needs to output a probability, 70%, 30%, whatever, and for that forecast to be actually useful, it absolutely must be calibrated.
Calibration feels like a really critical concept here. What exactly does that mean in the context of a
Oh,
forecast?
it's absolutely critical. Calibration means that if your model predicts something has, say, a 70% chance of happening, then over all the times it makes that 70% prediction, the event should actually happen roughly 70% of the time.
Okay, so the prediction matches the reality over time.
Precisely. If it says 70%, but the event only happens 50% of the time when it says that, it's poorly calibrated. It's overconfident. Good calibration builds trust. It's essential if you're actually going to use these forecasts to make real decisions, whether that's in finance, logistics, planning, anything.
So it's not just what it predicts, but how well it understands its own confidence in that prediction.
You nailed it. That's the essence. And this need for precise calibrated probabilities is a major driver behind the specific technical choices they made, especially when it came to evaluating success.
Okay, so we've got these big challenges, binary but delayed, noisy rewards, plus the critical need for calibrated probabilities. That sounds really tough for standard RL. So the study had to innovate, right? What were the core academic adaptations they made to existing RL algorithms like, say, GRPO and ReMax?
Yes, and this is where the academic side, the real innovation, gets quite interesting. They took two leading on-policy RL algorithms, GRPO and ReMax, and specifically modified them for this unique forecasting setup.
Okay, let's take GRPO first. How did they tweak that one? What was the modification?
So standard GRPO often uses something called per-question variance scaling. Basically, it normalizes the rewards or the losses within all the possible outputs generated for a single specific question.
Normalizes them, okay?
The researchers' adaptation, which they call modified GRPO, actually removed this scaling step completely.
Huh. Why remove something that sounds like it might help stabilize things? What was the logic there?
The core idea, the hypothesis really, was to preserve the raw magnitude of the really large forecast errors.
Ah, okay.
In forecasting, getting a probability wildly wrong, say predicting 10% when it should be 90%, can result in a very large Brier score loss, a big penalty. Standard variance scaling can kind of dampen or flatten these big penalty signals compared to smaller ones.
So it makes big errors seem less big.
Sort of, relatively speaking. By removing the scaling, they aim to let the algorithm really see and react more strongly to those extreme miscalibrations. The hope was this would improve its ability to fix them. They did note, though, that this can introduce some instability, which is a trade-off.
Interesting. So they were willing to maybe risk a bit of training instability to make absolutely sure the model felt the full sting of a really bad miscalibration.
That seems to be the thinking, yes. They wanted that error signal, especially the large ones, to come through loud and clear. Now, ReMax takes a different tack.
Okay, how does ReMax handle it?
ReMax doesn't use variance normalization in the same way. Instead, it uses a learned baseline to compute something called advantages.
A learned baseline, how does that help preserve the signal differently from just removing scaling?
Right, so with ReMax, instead of dividing the reward by some measure of variance, you subtract a learned estimate of what the expected reward should be for that particular prediction or question. The academic point here is that this method, using these baseline subtracted advantages, was also hypothesized to better preserve the impact of those large reward signals, those big Brier losses you get from significant miscalibration compared to the scaling methods.
So two different technical approaches, removing scaling in GRPO, using baselines in ReMax, but both aiming for the same goal, making the RL algorithm more sensitive to the scale of the forecasting error.
Exactly. Both are attempts to tweak how the algorithm interprets the feedback signal, making it pay more attention to those crucial large errors that really signify poor calibration or accuracy in forecasting.
Okay, so the algorithmic innovation is really centered on making sure the model feels the impact of getting probabilities significantly wrong. That sounds key for learning calibration in this noisy setup.
Precisely. It's all about engineering that learning signal to be as relevant as possible to the specific demands of forecasting. But, it wasn't just about the algorithms themselves. The right they conducted the training was also highly specific and I think quite innovative.
You mean that strictly online single pass protocol they used?
Yes, that was absolutely critical. It was a very deliberate methodological choice, mainly to prevent a specific kind of overfitting problem.
How did it work?
The model saw each forecasting question exactly once, in strict chronological order, and critically, only after the actual outcome of that forecast was known or resolved.
And the reason for being so rigid about that, one pass, chronological, only after the fact.
It was all about preventing the model from inadvertently learning about the future. If you trained it for multiple passes over the same data set, especially data where the outcome is now known, the model might start picking up on subtle correlations or patterns that simply wouldn't exist in a real forecasting situation where the future is genuinely unknown.
Right, it could learn to cheat by seeing the answers implicitly.
Exactly. By processing each question just once, after the outcome is known, but strictly in the order they occurred, they simulate the real-world flow of information and prevent that kind of look-ahead bias. It keeps the training honest.
That makes a lot of sense. And you mentioned earlier that removing scaling, like in modified GRPO, could cause instability. Plus, they were using a huge data set. Did they do anything else to manage the training process? You mentioned guardrails.
Yes, the guardrails, these were essentially lightweight penalties built right into the training process itself. They weren't overly complex, but targeted specific undesirable outputs.
Like what kind of outputs?
Things like the model generating nonsensical text, just gibberish, or including non-English text, or importantly, failing to provide a rationale alongside its probability prediction.
And these were essential because why made these extra penalties?
Because training RL on a large, inherently noisy data set that used up to 100,000 questions is just plain challenging. Without these guardrails, the researchers observed specific failure modes cropping up.
What kinds of failures?
Things like the model becoming wildly overconfident, just spitting out 0% or 100% probabilities inappropriately, or generating invalid text, like the gibberish or language switching. The guardrails acted like, well, guardrails steering the training away from these common pitfalls and making the whole process more robust and stable, especially when dealing with the complexities of this task at scale.
And the data itself, it was a mix of real-world market data and synthetic questions, but carefully handled.
Yes, they combined resolved questions from Polymarket, a prediction market, with synthetically generated forecasting questions. But they were very careful to ensure temporal consistency. Any external context provided to the model was strictly truncated cutoff at the time the forecast would have actually been made for that specific question. Again, anything to avoid that look-ahead bias.
Okay, so a really thoughtful setup. Adapted algorithms targeting the error signal, a unique training protocol preventing cheating, and guardrails for stability. How did they actually measure if all this academic effort, these innovations, paid off? What were the goalposts, the evaluation metrics?
They logically focused on the two core measures you need for probabilistic forecasts. One is accuracy, and the other is that crucial calibration piece.
Okay, accuracy first. They used the Brier score for that.
Correct. Specifically, the soft Brier score for the final evaluation. The Brier score basically measures the average square difference between the probability the model predicted and the actual outcome, which is represented as 0 or 1. So a lower Brier score means better accuracy, more accurate predictions.
Lower is better, got it. I think they mentioned a strict Brier too. Was that different?
Yeah, that was more of an internal training detail. The strict Brier applied the maximum possible penalty for any kind of malformed output during training, like if the model didn't output a valid probability. The soft Brier, used for evaluation, gave a fixed, less severe penalty for those malformed outputs.
Why the difference?
The strict Brier in training helped push the model away from generating garbage. But for evaluation, the soft Brier was seen as better because it didn't totally tank the score for a single bad output, preserving more signal about the model's overall predictive skill and avoiding score collapse. The key thing for you listening is Brier score measures accuracy, lower is better.
Makes sense. So Brier for accuracy. What about calibration, which we keep saying is so important? How did they measure that?
For calibration, they used a metric called expected calibration error, or ECE.
EC. Okay, what does that capture?
EC directly measures how well the model's stated confidence, its predicted probability, aligns with the actual frequency of events happening. So if the model says 70% many times, does the event actually happen about 70% of those times? A low EC means yes, the confidence matches reality, excellent calibration.
And a high ECE means it's poorly calibrated, over or underconfident.
Exactly. A high ECE means the probabilities it's giving aren't reliable. A low ECE is absolutely crucial for building a trustworthy, useful forecast. This metric really captures that vital aspect of the model, knowing how confident it should be.
And to see how good their models were, they compared them against some pretty tough benchmarks.
Yes, definitely. They compared their fine-tuned RL models against a leading frontier model at the time, OpenAI's O1 model, and they also compared it against the actual real-world market prices derived from Polymarket on a held-out test set of questions.
So comparing against both state-of-the-art AI and the collective intelligence, or maybe wisdom, of a real money market.
Precisely, setting a high bar for their results.
All right, the moment of truth then. Did these innovative methods, these academic tweaks, actually work? What did they find? Did the adaptations pay off in the results?
Yeah, the results were actually quite compelling, I'd say, especially when they scaled up the training data to that 100K question set and used ensembling, combining predictions from multiple training runs.
Okay, let's start with accuracy. How did they stack up on the Brier score compared to the benchmarks?
So their best performing configuration, which is a 7-run ensemble of the models trained using ReMax on the full 100K dataset, and with those guardrails active, it achieved a soft Brier score that was statistically indistinguishable from the frontier baseline, OpenAI O1.
Wow, okay, so a 14 billion parameter model fine-tuned with these specific methods could match the raw prediction accuracy of a potentially much, much larger state-of-the-art model on this forecasting task.
That's right, which is in itself a pretty significant result. It really demonstrates the power of this kind of targeted fine-tuning approach.
Matching accuracy is definitely impressive, but you emphasized calibration earlier as where the real academic innovation and practical value might lie. Was there a breakthrough on the ECE front?
Absolutely, and this, I think, is perhaps the standout innovative finding of the study. That same ReMax ensemble significantly outperformed OpenAI O1 in calibration.
Significantly outperformed. How much better?
It achieved an ECE of 0.042. Compare that to O1's ECE, which was 0.089. So the ensemble's calibration error was less than half that of the frontier model.
Less than half. That's a huge difference.
It is. And what's perhaps even more remarkable is that its calibration level, That 0.042 ECE essentially matched the calibration of the real money polymarket prices themselves, which came in at 0.0425 ECE on the same test set.
Whoa, so the AI model, trained this way, was as well calibrated as an actual prediction market with real money on the line.
Pretty much, yeah. Achieving that level of calibration with an AI forecaster is, I think, a major breakthrough demonstrated by these adapted RL methods. It's not just predicting, it's predicting with accurate confidence.
Matching real-world market calibration is genuinely huge, but metrics like ECE can sometimes feel a bit abstract. How did they show that this improved calibration wasn't just a nice score, but actually translated into something tangible, like, say, economic value?
That's a great question. They tackled that directly by evaluating the models using hypothetical trading simulations on Polymarket.
How did that work?
They simulated placing simple one-share trades based on the model's probability forecasts compared to the market price available at that time. The key concept they tracked was the model's expected edge, basically, the difference between the probability the model predicted and the probability implied by the market price.
Okay, so if the model was more confident than the market, that's positive edge.
Exactly. And then they tested if the superior calibration actually led to better simulated trading results.
And did the calibration turn into profit?
Yes, it really did. The studies found that this calibration advantage translated directly into significantly higher economic value in their simulations. They applied a simple but quite clever trading rule. What was the rule? They only simulated making a trade if the model's calculated expected edge was greater than its own estimated expected calibration area, the ECE. So the rule was essentially edge east.
Huh. So it's like a filter based on the model's self-awareness of its own potential calibration error. Only bet when your perceived edge is bigger than your known tendency to be wrong.
Precisely. It's a really neat way to leverage the calibration information. And using this rule, that highly calibrated ReMax ensemble generated $127 in hypothetical profit on the test set.
Okay, $127 profit. How did that compare to the baseline?
Significantly better. OpenAI's O1 model, using the exact same edge EC rule based on its own EC, generated only $92 in profit.
Wow, so the better calibration directly led to about 38% more profit in this simulation.
That's right. It clearly demonstrated that leveraging good calibration isn't just academically interesting. It's key to transforming raw forecasting skill into tangible economic value. It's not just about being right, it's knowing when you're likely right and how confident you should be, and then acting on that knowledge.
So the calibration essentially acts as a kind of profitability filter, screening out bets where the model might be less reliable even if it shows an edge.
That's a great way to put it. By filtering trades using the model's own estimated calibration error, they could capitalize on the genuine opportunities while smartly avoiding bets where the model's confidence might be misplaced.
Did they notice anything else about where that trading advantage came from?
Yes, they noted an interesting pattern. The trading advantage of their calibrated ReMax ensemble, when compared against just betting with polymarket prices, was particularly concentrated in what they called lower confidence markets specifically, where the polymarket price was below 65%.
So it found more value when the market itself wasn't overwhelmingly certain?
That seems to be the implication. It suggests these methods might be particularly adept at finding an edge in situations where the collective market judgment is less decisive or more uncertain.
And just quickly looping back those guardrails we discussed for training stability, did the results confirm they were effective?
Yes, the results suggested they were quite effective. They helped mitigate those specific failure modes. They were designed to prevent things like the model assigning extreme, unjustified 0% or 100% probabilities, and they also reduced the frequency of the model generating invalid or gibberish text. This made the overall training more stable and the final outputs more consistently reliable.
Okay, so zooming out from the specific results, what are the big picture takeaways here? Why does this particular study matter in the broader context of AI and forecasting?
I think this study carries some really significant implications. First and foremost, it demonstrates pretty convincingly that these carefully designed and adapted RLVR methods can actually be applied successfully to complex, messy, real-world tasks like forecasting. It extends RLVR's reach way beyond those clean, deterministic domains like math or code where it first proved itself.
So it shows RL can handle the noise and delay of the real world if adapted properly.
Exactly. It shows that the academic challenge of dealing with that delayed, noisy feedback and simultaneously meeting the need for precisely calibrated outputs is actually solvable. It requires the right algorithmic choices, like focusing on the reward signal magnitude, and the right methodological innovations, like that strict online training protocol.
And a key finding seemed to be that this wasn't just possible with some hypothetical, unimaginably huge model, right?
That's a really crucial point, I think. It shows that even a modest scale model, in today's terms a 14 billion parameter model, when fine-tuned using these specific innovative methods, can match or even exceed the performance of much larger frontier models on the metrics that really matter for forecasting, especially on calibration.
Which then translates directly into real economic value, as the trading simulation showed.
Precisely. It really underlines the idea that the method, the algorithmic adaptations, the training setup, the guardrails, matters just as much as, if not sometimes more than, just raw model scale, particularly for specialized applications like this. The authors themselves suggest that scaling these specific techniques up to much larger models is a very logical next step for future work.
This deep dive really illuminated how researchers are getting into the nitty-gritty, tackling the hard problems in AR, taking powerful techniques like RL, which work well in controlled environments, and figuring out how to make them genuinely effective for the unpredictable, messy reality of forecasting.
And by making those innovative academic adaptations to the algorithms and the training, they achieve breakthroughs not just in matching baseline accuracy, but maybe more importantly in achieving levels of calibration that rival real money markets.
Which, as we saw, unlocks that tangible economic value. It's a fascinating connection.
It really highlights that building trust in AI's predictions, making them truly useful, isn't just about getting the right answer more often. It's about the AI consistently knowing how confident it is and being demonstrably correct about that confidence level.
Absolutely. And just think about what that means for you, for all of us. Having access to AI that doesn't just predict, but predicts reliably with well calibrated confidence. How could that change decision making in areas like finance or managing supply chains or even climate modeling, or maybe just how we interpret the news about potential future events?
It definitely makes you consider a future where AI forecasting isn't just potentially accurate, but genuinely trustworthy and actionable because of that calibration.